and a 2-degree tilt across a distance almost impossible for the human mind to fully comprehend. It is worth mentioning here that Voyager 2 was not the only twin to face a crisis like this. A few months later, in late 2023 and stretching into 2024, Voyager 1 suffered its own emergency, a failing memory chip inside its onboard computer that caused it to transmit garbled, unreadable data for nearly 5 months straight. That problem was different in nature, an internal hardware failure rather than a simple orientation error, and it forced engineers to rewrite and relocate pieces of decades-old software remotely, using programming languages that had gone out of fashion before most of those engineers were even born. Both crises shared the exact same underlying fear. Every single step carried real weight because there was no repair crew waiting nearby and no way to physically inspect anything at all. Both crises, remarkably, ended in success. But here is where this story becomes something bigger than an engineering rescue. Because what Voyager 2 has been telling us, both before and after that frightening 2-week silence, is actively rewriting what scientists thought they understood about the edge of our solar system and the mysterious space that lies beyond it. Back on November 5th, 2018, when Voyager 2 first crossed the heliopause and entered true interstellar space, it carried something its twin no longer had working properly, a fully functioning plasma science instrument. Voyager 1 had crossed this same kind of boundary 6 years earlier, but the instrument specifically designed to measure plasma directly had already stopped working back in 1980, decades before that historic crossing even happened. Scientists still learned a great deal from Voyager 1's crossing using its other instruments, but they never received a direct, real-time reading of what the plasma itself was actually doing at that exact moment in that exact place. Voyager 2 finally gave scientists that missing piece. For the first time in human history, researchers had direct, real-time measurements of plasma on both sides of the invisible boundary between our solar system and interstellar space, recorded by an instrument that was physically passing through it as the data was collected. And what those measurements showed did not match the predictions that decades of careful modeling had produced. Scientists had expected this boundary, known as the heliopause, to be a slow and gradual transition, a wide zone where solar wind and interstellar plasma mixed together gradually across some meaningful distance. Instead, Voyager 2 recorded a transition that happened in less than a single day. It was almost a hard line rather than a blurry edge. Solar wind plasma on one side, interstellar plasma on the other. Sharp, sudden, almost like stepping through a doorway instead of slowly wandering through a foggy hallway that fades from one room into the next. The temperature of that interstellar plasma also surprised researchers considerably. The prevailing models had predicted it should be quite cold. What Voyager 2 actually measured was noticeably warmer than anyone had expected. And because its instrument was genuinely working, unlike the equivalent instrument on Voyager 1, scientists finally had real, concrete numbers to work with instead of indirect estimates and educated guesses. There was more waiting to be discovered. Just inside the heliopause, Voyager 2 detected something researchers now describe as a magnetic barrier, a region where the surrounding magnetic field suddenly grows dramatically stronger. This barrier plays a major role in controlling how cosmic rays, extremely high-energy particles that originate from distant exploding stars scattered across the galaxy, are able to enter our solar system in the first place. The exact way this natural shielding actually works turned out to be far more complicated and far more structured than anything scientists had modeled before Voyager 2 physically arrived there to check for itself. Here is something else worth sitting with for a moment because it changes the whole picture. Voyager 1 crossed the heliopause heading in a northern direction. Voyager 2 crossed it heading south at a completely different point along that same invisible boundary. If the bubble surrounding our entire solar system were a perfect symmetrical sphere, both crossings should have discovered nearly identical conditions on either side. They did not. Voyager 2 found a noticeably thinner boundary, different magnetic field strength, and plasma conditions that were measurably different from what Voyager 1 had experienced years earlier, at a different location entirely. This tells scientists something genuinely important about the nature of our cosmic neighborhood. The heliosphere, the giant protective bubble that surrounds our entire solar system, is not shaped like a perfect ball floating in space. It is stretched, compressed, and shaped unevenly by its constant, ongoing collision with the interstellar material pressing in from outside. And the only reason we know any of this at all is because 2 aging spacecraft, launched in the very same year nearly half a century ago, happened to cross that boundary in 2 very different places, at 2 very different times. It is strange to think that a discovery this significant hinged on nothing more dramatic than which direction a spacecraft happened to be traveling when it crossed an invisible line nobody can actually see. A few degrees of latitude, a different launch trajectory decades earlier, and we might never have known the heliosphere was lopsided at all. Sometimes, the biggest discoveries in science come down to details this small, sitting quietly in the data until someone finally notices them. Think about how fragile that knowledge really is when you stop to consider it honestly. There is no telescope on Earth, no matter how advanced, that can fully replace this kind of direct physical measurement. No computer model, no matter how sophisticated, can truly substitute for a real instrument sitting right there in that environment, recording what is actually happening in real time. And right now, today, there is no other spacecraft built, funded, or even seriously planned that is heading toward that same distant region to continue this work if Voyager 2 ever falls silent for good. That is what makes the July 2023 silence feel so much heavier than it might first appear on the surface. It was never just about losing a signal for 2 uncomfortable weeks. It was about the very real risk of permanently losing. The only living, functioning window humanity currently has into a part of the universe that keeps surprising every single model we have ever built to try to describe it. If you have made it this far, you clearly love stories like this one, so let us make it official. Subscribe now and tell me in the comments which fact in this video surprised you the most. I genuinely read every single one of them. The engineers who work on Voyager 2 today carry a strange and quiet kind of responsibility that few people outside their small community ever think about. Many of them were not even born when the spacecraft first launched back in 1977. They did not build it with their own hands. They inherited it, along with all of its history, its quirks, and its risks. They study old blueprints and outdated technical manuals written in programming languages that were already becoming obsolete decades before most of them ever entered the field. Before sending any command at all, no matter how small or routine it might seem, they test it first on an identical replica system, kept in a laboratory, because there's no possible way to physically inspect the real spacecraft, and there is absolutely no room for a mistake that cannot be undone. Every single year, Voyager 2 loses a small amount of usable power, roughly 4 watts annually, as the radioactive plutonium powering it continues its slow, steady, natural decay. To keep the mission alive for as long as humanly possible, engineers have had to make genuinely painful choices, switching off individual scientific instruments one at a time, permanently, simply to preserve enough remaining power for the instruments that are still left running. Each shutdown is completely final. There's no switching anything back on once that power has been redirected elsewhere. And yet, right now, at this very moment, while you're watching this video, Voyager 2 is still out there, still moving through interstellar space at roughly 34,000 miles per hour, still sending back data from an environment that no human being has ever visited in person, and almost certainly never will in any of our lifetimes. Every single measurement it manages to collect adds another piece to a picture of the universe that we simply cannot build in any other way, from any other source, using any other method available to us. At some point in the early 2030s, scientists expect that the remaining power will finally drop too low to keep any instruments running at all. When that moment eventually arrives, the signal will stop for good, not because of a software error, not because of a stray 2-degree tilt, but simply because the spacecraft will have quietly run out of the energy. It needs to keep speaking to us across all that distance. And this time, there will be no clever fix waiting in reserve, no powerful shout across the void, no second chance sitting somewhere in the back pocket of a determined engineering team, but the spacecraft itself will not actually stop moving. It will keep traveling onward in a straight, silent line, forever, long after every single engineer who ever worked on it has passed away. Attached to its side is a golden record, a message carefully chosen decades ago to represent all of humanity to whatever might one day find it, containing our music, our voices, our images, sent out into the endless dark on the small chance that something or someone out there ever discovers it, drifting past. One more thing before we get to the end of this story. If you have stuck around this long, you are exactly the kind of viewer this channel is built for. So do me one more favor, comment the word signal right now if you want more deep dives like this one, and I will personally make sure more of them come your way. There is something else worth understanding about why NASA fought so hard to save 14 days of contact with a machine most of the world has completely forgotten about. Voyager 2 was never designed with interstellar space in mind at all. Every part of it, every wire, every instrument, every line of its original software was built in the 1970s to survive a tour of 4 planets, not a multi-decade journey into the space between stars. Nobody sitting in that laboratory back then could have predicted that this particular machine would still be transmitting usable science data more than 4.5 decades later, from a region of the universe that did not even have a confirmed boundary at the time it launched. Every extra year Voyager 2 survives is, in a very real sense, a small miracle of 1970s engineering meeting, decades of careful, patient maintenance by people who refused to let it go quiet before its time. And there is a quieter kind of significance hiding underneath all of this too. Right now, humanity has no other mission on the drawing board that is heading toward interstellar space. Nothing currently under construction, nothing currently funded, nothing scheduled to launch in the coming years is aimed at reaching that same distant boundary anytime soon. Building something new and sending it that far would likely take decades just to plan, fund, and launch, and then several more decades of travel time before it ever reached the same distance Voyager 2 has already covered. Which means that for the foreseeable future, whatever Voyager 2 and Voyager 1 managed to send home before their power finally runs out may be the only direct data humanity has from that region for the rest of this century, and possibly longer than that. That is the real weight sitting behind those 14 days of silence in the summer of 2023. It was never simply about restoring a signal. It was about protecting what might be an irreplaceable, one-time opportunity, a narrow window that took nearly half a century to open, and that nobody currently alive will see reopened once it finally closes for good. For now, though, the signal is still coming. Voyager 2 is still talking, and everything it has told us since it briefly fell silent in the summer of 2023 has already reshaped how scientists understand the invisible boundary of our own solar system, along with the strange, warmer, sharper, and far more complicated region of space that lies just beyond it. Somewhere out past the reach of every planet you have ever heard of, a machine older than most of the people watching this video right now is still moving steadily through the dark, still listening for us, still speaking back. One faint radio wave at a time, across a silence so vast that even light itself needs a full day just to cross it from one end to the other. And one day, not too far from now, that signal will finally stop for good. But right now, tonight, in this exact moment as you're watching this, it has not stopped yet. It is still out there, still reaching back toward home. What if the most distant machine ever built by human hands suddenly stopped talking to us and nobody could reach out and fix it? For 14 days in the summer of 2023, that is exactly what happened, and the silence almost became permanent. Before we go further, hit that like button right now. It genuinely helps this channel more than you think. And if you are new here, subscribe and tap the bell, because stories like this one deserve to reach more people, not fewer. On July 21st, 2023, a spacecraft more than 12 billion miles from Earth stopped sending data. On July 21st, 2023, a spacecraft more than 12 billion miles from Earth stopped sending data. It was not destroyed. It was not lost. It was still flying, still alive, still moving through the black emptiness beyond our solar system at incredible speed. But the stream of information that had flowed home every single day for 46 straight years simply stopped, and nobody on Earth knew exactly why. That spacecraft was Voyager 2, and what happened to it that summer, along with what it revealed once contact was restored, is one of the strangest and most quietly emotional stories in the history of space exploration. It is a story about a machine older than most of the people who now care for it, a team of engineers who refused to let it die, and a discovery about our own solar system that nobody saw coming. To understand why this mattered so much, you first have to understand what Voyager 2 actually is. It launched in August 1977, just 16 days before its twin, Voyager 1. Both spacecraft were sent out on a rare mission window, a planetary alignment that happens only once every 175 years. This alignment allowed a single spacecraft to visit Jupiter, Saturn, Uranus, and Neptune. In one continuous journey, using each planet's gravity like a slingshot to fling itself toward the next one. Engineers in the 1970s knew they would not get another chance like this in their lifetimes, so they built two nearly identical explorers and sent them out into the unknown, hoping they would survive long enough to finish the tour. Consider what that actually meant for the people building it. There was no guarantee any of the technology on board would even survive the radiation and cold of deep space for more than a few years, let alone half a century. Every circuit, every wire, every tiny mechanical joint had to work perfectly, with nobody ever able to reach out and repair it once it left the launch pad. Nobody expected either spacecraft to survive this long. The original mission was designed to last around 5 years. Visit the planets, gather the pictures and readings, and then let the spacecraft drift quietly into the dark, somewhere past Neptune, its job finished. But Voyager 2 refused to cooperate with that plan. It kept going. It kept working. It kept talking to Earth, year after year, decade after decade, long after the scientists who built it had retired, and in some cases, long after they had passed away. It became something nobody had really planned for, a machine that simply would not stop. By 2018, something remarkable happened. Voyager 2 crossed the heliopause, the invisible boundary where the sun's influence finally fades away and true interstellar space begins. Only one other object made by human hands had ever crossed that line before it, and that was its twin, Voyager 1, 6 years earlier, in 2012. Voyager 2 became only the second human-made object in all of history to leave the protective bubble that surrounds our entire solar system and enter the space between the stars. Think about that for a moment. Everything you have ever known, every person, every building, every ocean, every sunrise, every single thing that has ever happened to you exists inside that bubble. Voyager 2 flew out of it. And it kept sending signals back, describing a place that no human eye has ever seen directly and likely never will in our lifetimes. Now here's the part that makes this story so tense, and why fixing a small problem out there is nothing like fixing a small problem here on Earth. Voyager 2 is so far away that even light, the fastest thing in the entire known universe, takes about 18 and a half hours just to reach it, and then another 18 and a half hours for a reply to travel back. That means every single exchange between Earth and the spacecraft takes at least 37 hours round trip, just for one question and one answer. You cannot call up and ask what is wrong. You send a message and then you wait. You wait almost 2 full days just to find out whether your message even arrived at all, let alone whether it worked. On that day, in July 2023, engineers at NASA's Jet Propulsion Laboratory were sending a routine set of instructions to Voyager 2, the kind of scheduled maintenance commands they had sent successfully thousands of times before without a second thought. But somewhere inside that sequence, something went wrong. A command was transmitted that should never have been sent, at least not in that exact form, and the result was devastating in its simplicity. Voyager 2's large dish antenna, the single piece of hardware responsible for both receiving instructions from Earth and sending all of its scientific data home, tilted 2 degrees away from Earth. 2 degrees sounds like nothing at all. If you tilt your head 2 degrees right now, you probably would not even notice the difference. But at a distance of over 12 billion miles, 2 degrees is the difference between hitting a target and missing it completely. Earth, seen from Voyager 2's position, is an impossibly tiny point of light lost in an ocean of darkness. The antenna has to aim with extraordinary precision just to keep the connection alive, and a 2-degree error was more than enough to break that connection entirely. And here is the cruel twist that made this situation so much harder than a normal technical fault. The very antenna they needed in order to fix the problem was the same antenna that had just turned away from them. To send a correction, they needed the spacecraft to hear them clearly. But the spacecraft could no longer hear anything properly, because its ear, in a very real sense, was now pointed in the wrong direction, out into empty space instead of toward home. The team had 2 real choices in front of them. Voyager 2 has a built-in safety feature, a kind of automatic reset that happens a few times every year, where the spacecraft realigns its antenna with Earth just in case something exactly like this occurs. That reset was scheduled for October 15th, months away. If the engineers did absolutely nothing, the spacecraft would almost certainly correct itself eventually, on its own, without any help at all. But months of silence meant months of lost data from a region of space that no other machine on Earth has ever been able to study directly. And there was no guarantee that everything on board would still be functioning correctly by the time October finally arrived. The project manager overseeing the mission, Suzanne Dodd, described their other option honestly, without sugarcoating it. They could attempt something far riskier. Aim one of the most powerful transmitters on the entire planet directly at the spacecraft's last known position, and hope, simply hope, that the signal was strong enough to reach an antenna that was no longer pointed at them at all. She admitted openly to reporters that the odds of this working were low, not impossible, just low. And in a mission like this one, low odds are still worth attempting when the alternative is months of silence and uncertainty. Before they tried anything drastic, though, the team needed to answer one question first. Was the spacecraft even still alive out there? On August 1st, using multiple stations from NASA's Deep Space Network, engineers listened carefully for what is called a carrier signal, a faint, steady radio hum that any functioning spacecraft continuously gives off even when it cannot send readable data. Think of it like a heartbeat monitor in a hospital room, a signal that simply says, "I am still here," even if it cannot say anything more detailed than that. They found it. Faint, much weaker than normal, because the antenna was misaligned, but it was unmistakably there. Voyager 2 was alive. Its hardware was intact. They found it. Faint, much weaker than normal, because the antenna was misaligned, but it was unmistakably there. Voyager 2 was alive. Its hardware was intact. It simply could not hear them clearly, and it could not speak clearly either. Picture the engineers gathered around their monitors that morning, watching a screen that had shown nothing but flat, empty static for 11 straight days. Then faintly, a tiny rise in the noise floor, a whisper hiding inside billions of miles of silence. It was not much. It certainly was not data, but it was proof of life. And after nearly 2 weeks of uncertainty, proof of life was worth more than anything else in that moment. That discovery changed everything about the plan going forward. If the spacecraft was healthy and its systems were still functioning, then the only real problem was the angle of a single antenna, nothing more catastrophic than that. And if a faint signal could travel all the way from Voyager 2 to Earth and still be detected, then maybe, just maybe, a powerful enough signal could travel the opposite direction and actually be received. Quick pause here. If this story is pulling you in, do something small for me right now. Share this video with one person who loves space, science, or just a good true story. It costs you nothing, and it means everything to a channel like this one. Now let us talk about the infrastructure that made any of this even remotely possible, because it deserves its own moment of appreciation. The Deep Space Network is a global system of enormous radio antenna stations, positioned at 3 locations around planet Earth, one in the Mojave Desert in California, one near Madrid in Spain, and one near Canberra in Australia. These 3 locations are spaced deliberately, roughly 120 degrees apart around the globe. As the Earth rotates, at least one of these 3 stations always has a clear, unobstructed line of sight toward any spacecraft flying through deep space. The planet itself, in a sense, never fully turns its back on these missions. Each station houses multiple massive dish antennas, the largest of which stretch 70 meters across. These are among the most sensitive radio receivers ever built by human beings, capable of detecting signals so faint they are almost impossible to imagine. Electromagnetic whispers that have traveled across billions of miles of empty space to reach them. On August 2nd, 2023, engineers chose the Canberra station specifically because its position in the southern hemisphere gave it the best possible geometric angle toward Voyager 2's current location in the sky. Using that enormous dish and a transmitter powerful enough to be measured in the hundreds of kilowatts, engineers aimed everything they had at a single, precise point in space. The last known orientation of a spacecraft whose receiving antenna was tilted the wrong way, across a gap of more than 12 billion miles. And they sent one very simple instruction, wrapped inside all that raw power: turn back toward Earth. Then they waited, 18.5 hours for the signal to arrive. Then, if everything worked as hoped, additional time for the spacecraft to receive the instruction, process it internally, and physically rotate its antenna into position. Then another 18.5 hours for any resulting response to travel all the way back home. In total, the earliest possible moment they could know whether it had worked was roughly 37 hours later. And even that number was not fully guaranteed, because nobody knew exactly how long the spacecraft itself would take to react once it received the command, assuming it received the command at all. Try, for a moment, to imagine being one of those engineers. You have spent years, sometimes entire decades, working closely with this specific machine. You know its habits, its quirks, its long and unusual history. And now you have done everything within human power to fix it, and there's genuinely nothing left to do but sit in a quiet room and wait for a signal that might simply never come. At 12:29 in the morning on August 4th, 37 hours after that command had been sent, something finally appeared on the screens at Mission Control. Data. Real, readable, meaningful data flowing steadily in from Voyager 2. The antenna had turned. It was pointing at Earth once again. The spacecraft was talking to them, almost as if nothing unusual had ever happened at all. The relief inside that room was reportedly immediate and completely genuine, the kind of relief that only comes after days of quiet, private dread. Suzanne Dodd later said something that captured the strange emotional bond these engineers have with a machine most people on Earth have never even heard of. She said that having Voyager 2 back online felt like getting a member of the team back, not a device, not a piece of equipment. A team member, 14 days. That is how long the silence lasted, from the moment the command error first occurred to the moment full communication was completely restored. 14 days out of 46 years of nearly unbroken conversation between Earth and this single spacecraft. It was the longest gap in the entire history of the mission. And it very nearly became permanent, not because the spacecraft itself was broken beyond repair, but because of one misfired instruction.